Inside an observatory, a small team of German astronomers is doing something that sounds almost impossibly tedious. They are counting stars, one by one. Every single point of light that passes through the eyepiece gets a number, written down by hand into an enormous catalogue. There is no photography helping them, just eyes, clocks, and paper. On one of those nights, a faint orange point of light drifts through the field of view. It is dim. It becomes the 5055th star counted in one narrow band of the southern sky, and it receives a designation so dry that no human being could ever love it. The astronomers log it and move on. They have thousands of stars left to count. What none of them can know is this: that faint orange dot is not ordinary. It only looks that way because of an almost unimaginable distance, and because it is hiding behind a curtain of cosmic dust. Because when we finally measure this star properly, the numbers that come back will sound like a mistake. A star so vast that if it traded places with our Sun, its surface would not stop at Mercury. Its glowing edge would keep going past Mars, past the asteroid belt, out toward the giant planets, until every world our ancestors ever knew was no longer orbiting a star, but buried somewhere inside one. And in that same small patch of sky, the constellation of the Shield, there is a second giant waiting, one that may be nearly impossible in size, a star that, by some measurements, should not even be able to exist. This is the story of how we found them, how we measured them, and why even now we cannot fully believe our own numbers. So here is what we know. UY Scuti sits in the constellation Scutum, a few degrees north of a star called Gamma Scuti, and just northeast of the Eagle Nebula. Recent measurements place it roughly 5,900 light-years away from Earth, buried deep inside the disk of our own Milky Way galaxy. Now, you might expect that one of the largest known stars in the universe would blaze in our night sky. It doesn't. Even at its brightest, UY Scuti only reaches around 9th magnitude, far too faint for the naked eye. You need a telescope just to find it, and that's because of where it lives. UY Scuti sits inside a region astronomers call the Zone of Avoidance, a band of sky where the dust and gas of the Milky Way's own disk block our view, like trying to see a lighthouse through fog. The star is also wrapped in a shroud of its own making, a thick, complicated cocoon of gas and dust that it is constantly shedding into space. It is, quite literally, a giant hiding behind a curtain. But even through all of that dust, one thing was clear from the very beginning. This star pulses. Its brightness swings between magnitude 8.29 and magnitude 10.56 in a slow, breathing rhythm, a semi-regular pulse with a period of roughly 740 days. Imagine a heartbeat that takes 2 years to complete. That's UY Scuti. The star is not steady. It swells and shrinks, brightens and dims, over and over, like something enormous slowly inhaling and exhaling in the dark. For more than a century, that was pretty much all we knew. A dim, dusty, pulsing red star in the Shield. Then, in the middle of 2012, everything changed. High in the Atacama Desert of Chile, astronomers pointed the Very Large Telescope at 3 red supergiant stars near the direction of the galactic center. They used a technique called interferometry, combining light from separate telescopes to measure details far too small for any single mirror to resolve. The 3 targets were AH Scorpii, KW Sagittarii, and UY Scuti. The results came back. And all 3 stars were monsters. Every one of them measured over 1,000 times bigger than the Sun. Every one of them shone more than 100,000 times brighter. But one of them stood apart. Of the 3, UY Scuti was the largest. It was the most luminous, and it was the coolest. The measurement said its radius was around 1,708 times the radius of the Sun. Let that number sit for a moment. 1,700 times wider than our Sun. Because if that figure is correct, it means something genuinely difficult to comprehend. If you lifted UY Scuti up and placed it at the center of our solar system, its surface would not stop at Mercury. It would not stop at Venus, or Earth, or Mars. Its glowing outer edge would reach nearly 8 astronomical units out from the center, almost 8 times the distance between the Earth and the Sun. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, all of it. Inside the star, our entire world, every ocean, every mountain, every person who has ever lived would be orbiting somewhere deep within the body of UY Scuti, dissolved into its interior like a grain of salt dropped into a furnace. Based on that 2012 measurement, UY Scuti was calculated to shine around 340,000 times brighter than the Sun, with a surface temperature of only about 3,365 Kelvin, remarkably cool for a star. Its initial mass was estimated at roughly 25 times the mass of the Sun, and possibly as high as 40. That single measurement is what made UY Scuti famous. It began to be described as the largest star known to science. It became the example used everywhere to illustrate the scale of the universe. But here's the strange part. That famous number 1708 was standing on surprisingly shaky ground, and within a few years, it would start to fall apart. Before we get to what went wrong, we need to answer a more basic question. How does a star even get this big? Because UY Scuti was not born this way. Based on our current models of stellar evolution, UY Scuti began its life as a hot, massive, relatively compact star, fusing hydrogen in its core the same way our Sun does. Its position deep within the Milky Way's disk suggests it formed rich in heavy elements, a metal-rich star, in the language of astronomers. But massive stars live fast. They burn through their fuel at a ferocious rate. And what we are looking at today is a star that has already moved past the first chapter of its life. Right now, the models tell us UY Scuti has begun fusing helium in its core, while a shell of hydrogen continues to burn around that core like a ring of fire. And when a star reaches this stage, something dramatic happens to its structure. The outer layers swell. They expand outward to almost absurd proportions, growing thinner and cooler as they stretch, until the star becomes a vast, puffy, glowing sphere of tenuous gas, a red supergiant. The surface cools into deep orange and red. The star becomes enormous, but also fragile. Its outer layers are held so loosely that they are barely attached to the star at all. So a natural question follows. If dying stars swell like this, is there a limit? Can a star just keep expanding forever? The answer is no. And the reason comes from a quiet piece of theoretical work published in 1961 by a Japanese astrophysicist named Chushiro Hayashi. Hayashi worked out something subtle and powerful. For any star of a given mass that is in balance, where the inward crush of gravity is exactly matched by the outward push of its own gas pressure, there is a boundary it cannot cross. On the great chart astronomers use to map all stars, a diagram comparing surface temperature against brightness, that boundary forms a nearly vertical wall at very low temperatures, down around 2,500 Kelvin. On one side of that wall, stars can exist in stable balance. On the other side lies what astronomers describe, quite literally, as a forbidden zone. The physics comes down to how energy moves inside a star. The cooler and more swollen a star becomes, the more its interior churns enormous currents of hot gas rising while cooler gas sinks, a process called convection. Hayashi showed that a fully convective star in equilibrium simply has no stable configuration beyond that wall. The models don't just become unlikely there. They stop existing entirely, and if a star somehow finds itself pushed across the limit, it doesn't get to stay. Massive temperature differences drive violent convection through its interior. The star becomes unstable, and it rapidly adjusts itself, shifting its structure until it settles back onto the boundary. That line is now called the Hayashi limit. And remarkably, it went unrecognized until 1961. partly because the calculations behind it required numerical methods that simply hadn't been developed earlier. One of the most fundamental rules governing every giant star in the universe sat undiscovered until the space age had already begun. There are exceptions, collapsing protostars that haven't yet found their balance, and stars with strong magnetic fields that interfere with convection. But for a mature red supergiant, the rule holds. Gravity and gas pressure draw a hard line across the sky and say, this far and no further. Keep that limit in mind. Because later in this story, we are going to meet a star that appears to be standing on the wrong side of it. And there's one more thing worth holding on to here. Every star that swells to these proportions is doing so for the same reason. It is running out of fuel. This isn't growth. It's a slow motion ending. And one day, a very long time from now, a much smaller and much quieter star is going to begin this exact same process. Ours. But we'll come back to that. Let's return to UY Scuti, because the closer we look at this star, the stranger it gets. UY Scuti is not just large, it is actively coming apart. The star is shedding its own substance into space at an extraordinary rate, on the order of several hundred thousandths of the sun's entire mass every single year. That may sound small. It is not. A flow like that, sustained over time, is what builds the vast, complex envelope of gas and dust that now surrounds the star, the dusty shroud we have to peer through just to see it at all. And inside that shroud, something remarkable is happening. Radio astronomers listening to UY Scuti have detected masers, naturally occurring beams of amplified microwave radiation produced by molecules of water, silicon monoxide, and hydroxyl in the gas around the star. Think of a laser, but built by nature out of a dying star's own exhaled breath, broadcasting in microwaves across thousands of light years. Now, these masers are real, but they are comparatively weak, not strong enough for UY Scuti to join the exclusive club of the most extreme dust-shrouded supergiants, like VY Canis Majoris. Astronomers have instead compared it to another cool, pulsating supergiant called S Persei. Sometimes UY Scuti is classified as a red supergiant, sometimes as an extreme red supergiant, sometimes as a hypergiant. The truth is, this star sits awkwardly between categories, as if it hasn't quite decided what it wants to be. Even its mass is a mystery. UY Scuti has no known companion star, and that matters, because a companion is one of the most reliable tools astronomers have for weighing a star. You watch how two objects pull on each other, and the orbit reveals the mass. With no partner, UY Scuti keeps its weight a secret. On theoretical grounds, its mass today is expected to sit somewhere between 7 and 10 times the mass of the Sun. Yet the 2012 study implied it began life at around 25 solar masses. If both of those figures are even close to correct, then this star may have already thrown away more than half of everything it ever was, scattered into the dark, one breath at a time. So, what does that mean? It means UY Scuti is not a stable monument. It is a process, a slow, luminous act of disintegration that has been running for ages and will not stop until the star itself is gone. Now we arrive at the problem. The one hiding underneath that famous number. When the Very Large Telescope measured UY Scuti in 2012, what it actually measured was an angle, the tiny sliver of sky that the star's disk covers, as seen from Earth. To turn that angle into a physical size, you need one more ingredient. You need the distance. And here's the uncomfortable truth. In 2012, nobody actually knew how far away UY Scuti was. The distance the team adopted, around 9,500 light-years, traced back to a study from 1970 based on modeling the star's spectrum. It was, at the time, the best available estimate, but it was an assumption, sitting quietly underneath the most spectacular measurement in stellar astronomy. And if the distance was wrong, then the size was wrong too. Then came Gaia. Gaia is a space observatory built to do, with breathtaking precision, exactly what those astronomers in Bonn were doing by hand in 1860, mapping the stars. It measures parallax, the tiny apparent wobble of a star against the background sky as the Earth swings around the Sun. From that wobble, you get distance, directly. No modeling, no assumptions. In Gaia's second data release, the parallax for UY Scuti implied a distance of only about 4,900 light-years, roughly half of what the 2012 study had assumed. Do the geometry, and the consequences are brutal. If UY Scuti is that close, then its radius collapses from 1,708 solar radii down to around 755. Its luminosity falls from 340,000 suns to roughly 87,000. The largest star ever measured would suddenly be not that, not even close. But here's the weird part. The Gaia measurement itself might not be trustworthy either. UY Scuti's parallax data carries a very high level of astrometric noise. The star's dusty, churning, swollen envelope makes it a genuinely difficult target to pin down. So astronomers found themselves in a strange position. Two answers, and good reasons to doubt both of them. In 2021, researchers attacked the problem again, combining Gaia's newer data with the star's color and apparent brightness. Their answer landed in the middle, about 5,900 light-years, and in 2023, a new measurement drawing on that distance settled on a radius of roughly 909 times the radius of the Sun, with a luminosity around 124,000 suns, and a surface temperature near 3,550 Kelvin. So think about what just happened here. Between 2012 and 2023, UY Scuti shrank by nearly half, not physically. The star itself never changed. What changed was us, our instruments, our methods, our honesty about what we actually knew. And to be clear, even the reduced figure is staggering. At 909 solar radii, UY Scuti still holds a volume around 750 million times that of the Sun. Placed at the center of our solar system, its glowing surface would still extend past the orbit of Mars, perhaps even out into the asteroid belt. Mercury, Venus, Earth, Mars, all still consumed. Our planet would still be orbiting inside a star. But the crown? The title of largest known star? That, quietly, had already begun slipping away. Because while everyone was watching UY Scuti shrink, another star was waiting in the exact same constellation. A star with a far messier story. And a size so extreme that many astronomers refuse to believe it. The year is 1990. An American astronomer named Charles Bruce Stephenson is working through data from a deep infrared survey of the sky light at wavelengths our eyes cannot see. And in the constellation Scutum, the same shield of stars that hides UY Scuti, he finds something unusual, a tight group of stars burning exceptionally bright in the infrared. It is an open cluster, a family of stars born together from the same cloud of gas and dust. It gets catalogued under his name, Stephenson 2. The discovery goes completely unnoticed by the public. But for astrophysics, it turns out to be crucial, because Stephenson 2 and other clusters nearby are not ordinary stellar families. They are graveyards of giants, regions crowded with red supergiants, massive stars swollen to monstrous proportions in the final stages of their lives, waiting to explode. And inside that graveyard, one star stood out immediately. When the first detailed analysis of the cluster was carried out in 2007 by a team led by an astronomer named Davies, this star was simply assigned the number 1. It was the brightest thing in the region. But almost from the first look, the researchers noticed something off about it. It sat at the edge of the cluster, not the middle. It was abnormally bright, suspiciously bright, even for a red supergiant. and its motion across the sky was slightly atypical. From the very beginning, this object looked like an outsider, a stranger who didn't quite belong to the community it appeared to live in. The team's initial conclusion was that it probably wasn't a cluster member at all, just a solitary giant that happened to sit along the same line of sight. Then the catalogs made everything worse. In a later study, the very same star was assigned a different number 18 and grouped with stars on the cluster's outskirts. That designation, popularized in 2010 by an astronomer named Deguchi, gave the star the name most people know today, Stephenson, 2-18. But to avoid the confusion of one star carrying two numbers, the scientific community settled on a more precise name drawn from the 2007 study, Stephenson 2DFK1. One star, three names, and that identity crisis on paper turned out to be a perfect preview of the identity crisis in the sky, because nothing about this star adds up. Start with the distance. When Stephenson discovered the cluster in 1990, he estimated it lay about 98,000 light-years away, practically at the edge of the galaxy. In 2007, the Davies team used the cluster's motion through space to recalculate, and the answer dropped dramatically, roughly 19,000 light-years. A 2010 study found a similar figure and placed the star within the Scutum-Centaurus arm of the Milky Way, and that neighborhood of values is what's generally used today. But the researchers themselves have been unusually honest about how fragile this is. In work from 2012, the uncertainty in the distance was acknowledged to exceed 50%. It's like knowing a city is about 4 hours away with a margin of error of more than 2 hours. And remember what we learned from UY Scuti: if the distance is soft, everything built on top of it is soft too. Now, the brightness. The first estimates, based on a narrow slice of infrared light, suggested this star shines about 90,000 times brighter than the Sun. Respectable, but not shocking. Then, in 2012, a team modeled the star's full energy output across all wavelengths, and the number exploded to nearly 440,000 suns. And it didn't stop there. In 2020, a study led by the astronomer Humphreys integrated all of the star's emissions and arrived at 630,000 times the luminosity of the Sun. To put that in perspective, if our Sun were a single 100-watt light bulb, Stephenson 2DFK1 would be a lighthouse burning with the power of 63 million of those bulbs. And the authors of that study added a quiet, remarkable warning. The star's light behaves in a peculiar way. It doesn't follow the standard rules for how interstellar dust dims starlight, which means the true luminosity might be even higher. Then there's the temperature. Analysis of the star's spectrum, including the chemical fingerprint of titanium oxide, a telltale signature of cool stars, points to a surface temperature of only around 3,200 Kelvin. That is unusually cold, even for a red supergiant. And now, the callback. Remember the Hayashi limit? Remember the forbidden zone? Stellar evolution theory predicts that red supergiants should not be able to get cooler than roughly 3,500 Kelvin. Stephenson 2DFK1 appears to sit below that line. If that measurement is right, it may mean this star is not in equilibrium at all, that its own gravity can no longer stably contain its swelling. A star, in other words, standing inside the forbidden zone. A place where, according to theory, no stable star should be able to exist. Which brings us to the number this entire story has been building toward. In 2012, combining that enormous luminosity with that impossibly low temperature, researchers calculated the radius of Stephenson 2DFK1. The answer was 2,150 times the radius of the Sun. Stop. Sit with that for a second. 2,150. If this star traded places with our Sun, its surface would extend 1.5 billion kilometers out into space. 10 astronomical units. For comparison, Saturn, with its rings, its dozens of moons, its entire miniature system orbits at 9.59 astronomical units. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn. Every world that humans gazed at for all of recorded history before the invention of the telescope, every planet our ancestors ever knew existed, would be gone. Not orbiting the star, inside it, swallowed whole by a single ball of glowing gas with room to spare. And yet, that figure of 2,150 solar radii is larger than what theoretical models say should even be possible. The predicted ceiling for the biggest red supergiants sits around 1,500 solar radii. So the estimate itself may simply not be reliable, inflated by that 50% distance uncertainty, by the peculiar behavior of the star's light, by everything we still don't know. Which leaves us with an almost absurd situation. The star that might be the largest ever found is also the star whose measurements we trust the least. There's one more thing about Stephenson 2 DFK, one that we need to talk about, because like UY Scuti, this star is not simply sitting there being enormous, it is eating itself. The star is estimated to be shedding roughly 100,000th of the Sun's entire mass every single year, one of the highest mass loss rates ever recorded for any red supergiant. We know this because of its maser emissions, those natural microwave beacons again, this time from water and silicates in the material streaming away from the star. And the pattern of that outflow suggests something unsettling. This is probably not a smooth, gentle wind. The star appears to be unstable, likely ejecting its outer layers in violent, episodic convulsions. As far back as 2007, researchers noted that its excess infrared glow could mean the star is on the verge of shedding its outer layers entirely, transforming into something hotter and stranger, a luminous blue variable perhaps, or a Wolf-Rayet star, a stripped, screaming stellar core exposed to space. Then there's the final unsolved question, the one astronomers still argue about. Is Stephenson 2 DFK1 actually a member of the Stephenson 2 cluster at all? Or is it an imposter, a solitary titan that merely appears from our vantage point to stand among that family of giants? The case for membership goes like this. Yes, the star's velocity differs from the cluster average, but that difference could be an illusion. The star may be wrapped in a dense, expanding envelope of gas that distorts our measurements of its motion. It might also belong to a subgroup on the cluster's outskirts, sitting at the same distance as the main family. But in 2013, a study analyzed the star's maser emissions and infrared absorption features and reached a firm conclusion. Its velocity differs too much. By that reading, Stephenson 2 DFK1 is a field star, a loner, unrelated to the graveyard of giants it appears to haunt. The debate is not settled, the queen of the cluster, or a ghost passing through it. After more than 3 decades of study, we genuinely do not know. At this point, you might be asking a very reasonable question. Why is this so hard? We can weigh distant galaxies. We can photograph black holes. Why can't we just measure a star? The answer reveals something profound about what these giants actually are. A red supergiant has no surface. There is no edge, no boundary where the star stops and space begins. The outer layers are so thin, so distended, that the star simply fades away gradually from dense gas to thin gas, to wind, to nothing. Asking where such a star ends is a bit like asking where a candle flame ends, or where fog stops being fog. So astronomers use a definition. The sizes we've been discussing are based on something called the Rossland radius, roughly, the depth at which the star's atmosphere finally becomes opaque. The layer where, if you were falling inward, the haze would at last close up around you and you could no longer see out. That's the surface. It's a choice, a sensible one, but a choice. And that's why the title of largest known star is less like a fixed record and more like a crown passed around in the dark. UY Scuti held it for years, based on a number that later dissolved. Stephenson 2 DFK1 claims a size that theory says shouldn't exist. Other contenders crowd the leaderboard, each with its own contested measurements. VX Sagittarii, Mycephae, VY Canis, Majoris, WOHG 64, a giant so far away it isn't even in our galaxy, but in the Large Magellanic Cloud, and NML Cygni, which by some estimates reaches around 2,800 solar radii, potentially dwarfing them all. Every one of these stars is a candidate. Every one of these measurements has an asterisk. But here's what does not carry an asterisk. Whichever of these giants is truly the largest, all of them are large enough to erase a planetary system. All of them, placed where the sun now sits, would swallow the Earth without registering the event at all. So that raises a darker, more intimate question. What does it actually look like when a star swallows a planet? For most of history, that question was pure theory. Then, in 2020, we watched it happen. At the California Institute of Technology, an instrument called the Zwicky Transient Facility scans the sky every single night, hunting for stars that suddenly change in brightness. In 2020, it caught one. Somewhere in the disk of the Milky Way, in the direction of the constellation Aquila, a star brightened by a factor of 100 in the space of about a week, and then began to fade. A graduate student named Kishalay Dur found it in the data, and at first, he thought he knew exactly what it was. He wasn't even looking for anything exotic. He was hunting novae, a relatively common kind of stellar explosion that happens when a dead star steals fuel from a companion. This flash looked like a routine catch, except it wasn't. When Dee examined the light with the Keck Observatory in Hawaii, a nova should have revealed hot, glowing gas. Instead, the spectrum showed the signature of cool gas, including molecules that can only exist at very cold temperatures. By his own account, he couldn't make any sense of it, so he did something very human. He set the mystery aside, finished his PhD thesis, and moved on to a new position. About a year later, now at MIT, he came back to it. And this time, he and his colleagues looked at the star in infrared light, the wavelength of cold, hidden things. What they found changed everything. The brief flash of visible light had been accompanied by an extraordinarily bright infrared glow that faded slowly over 6 months. The star was manufacturing enormous quantities of dust. Then came the final clue, from a NASA space telescope called NEOWISE. It showed the star had actually started brightening in the infrared 9 months before the visible flash. And when the team added up the total energy of the entire event, the number came out strange, tiny. About 1,000th the energy of any stellar merger ever observed, which meant that whatever had plunged into this star was about 1,000 times smaller than a star. And it just so happens that there is a very familiar object with about 1,000th the mass of the Sun, Jupiter. This was a planet, a gas giant, roughly the size of Jupiter or smaller, crashing into its own sun. The star, an aging sun-like star roughly 10 billion years old, had slowly puffed outward as it began its transformation into a red giant, creeping closer and closer to its innermost planet. Friction dragged the planet into a death spiral. It skimmed the star's surface, pulling off hot gas that drifted outward and cooled into dust. And then it plunged into the core and was swallowed whole. The star flared, blew off material, and briefly swelled to 4 times its size. The event was named ZTF SLRN 2020. Published in the journal Nature in May of 2023, it stands as the first direct observation in human history of a star engulfing a planet. One of the study's co-authors called it a missing link in our understanding of the fates of solar systems, including our own. And based on the energetics, the researchers estimated that events like this quiet, faint flashes of a world being eaten happen in our galaxy somewhere between once every 10 years and several times per year. Which means that, as you watch this, somewhere in the Milky Way, this is probably happening again. Here's the problem though. Engulfment is fast. Astronomically speaking, the whole process can take just days or weeks. Catching one in the act, the way ZTF SLRN 2020 was caught, requires almost miraculous luck. So, astronomers developed a second approach. If you can't witness the crime, you look for the evidence left behind. In June of 2026, a team of 14 researchers from the United States and Chile published a study of a star called TOI 5882, a star nearly identical to our Sun, sitting about 1,300 light-years away. And the study made a striking claim. This star has almost certainly eaten one of its own planets. The evidence is a single chemical element: lithium. The lead author, a University of Michigan graduate student named Brooke Cotton, explained the logic with a phrase that's hard to forget. You are what you eat. Planets are heavily enriched in lithium. Stars are not the intense heat inside. A star destroys lithium over time, so a mature star should have almost none of it left. If you find a Sun-like star suddenly flush with lithium, that lithium probably came from outside, from something the star swallowed. And TOI 5882 is flush with lithium. When the team analyzed its light using a spectrograph in Arizona and compared it against a control lineup of more than 60 similar stars, TOI 5882 ranked in the 98th percentile for lithium enrichment. The signal was robust. The researchers noted that no matter how you slice the data, the star stood out. Elements associated with rocky material appeared elevated too. Based on the amounts involved, the team estimates the devoured world had a mass somewhere between a couple of Earths and Neptune. But here's what makes this case genuinely strange. TOI 5882 hasn't swollen into a red giant. Its radius is only about twice that of the Sun. Standard stellar evolution says a star at this stage shouldn't be swallowing anything. So how did the planet fall in? The team suspects the star had an accomplice. Orbiting TOI 5882, circling it once every 7.1 days, is a brown dwarf, a ball of gas more than 20 times the mass of Jupiter, yet still too small to ignite as a star. An object that heavy, orbiting that close, can gravitationally torment the smaller worlds around it. Over time, the researchers propose, it may have destabilized an inner planet's orbit and shoved it into a death spiral toward the star. The planet was torn apart, and its elements, lithium included, were stirred into the star's outer layers like evidence dissolved in acid. Cotton, it turns out, grew up dreaming of becoming a private investigator. She has said the field feels exactly like detective work. You can't watch the crime happen, so you assemble the clues and figure out who did it. And the clues keep coming. In a separate 2026 study, researchers examining red dwarf stars, stars far smaller and cooler than our Sun, found 6 of them. In 3 young star clusters, carrying lithium they simply should not have. The leading explanation is the same. Each of those small stars appears to have consumed several Earths' worth of planetary material. Step back, and a pattern emerges. Giant stars swallow planets by expanding into them. Sun-like stars swallow planets with the help of massive companions. Even the smallest, dimmest stars in the galaxy appear to swallow planets. By some estimates, roughly 30% of Sun-like stars will engulf at least one of their planets during their lifetimes. This is not an anomaly. It's a habit. Across the galaxy, quietly and routinely, stars eat their own worlds. And that brings us home, because there is one more Sun-like star we haven't talked about. In roughly 5 billion years, our Sun will exhaust the hydrogen near its core. The core will contract, the outer layers will swell 100, perhaps 1,000 times the Sun's current diameter as it becomes a red giant. The same transformation we have watched, frozen at different moments, in UY Scuti, in Stephenson 2DFK1, in the star that consumed its planet in 2020. Mercury will be the first to go. Then Venus. Earth's fate is genuinely uncertain. As the sun swells, it will also shed mass, loosening its gravitational grip, and the orbits of the planets will drift outward, a race between an expanding star and a retreating world. Earth might escape the surface of the sun. It might not. But the models agree that long before any final plunge, the heat alone will have ended everything here. The oceans, the atmosphere, every trace of the world we know. The lead researcher behind the 2020 engulfment discovery offered a haunting way to think about it. If someone were watching our solar system from thousands of light years away on that far future day, they would see almost exactly what we saw in 2020. A faint, brief flash in the dark. A little more subdued, perhaps, and then nothing. Somewhere out there, 5 billion years from now, our entire story could be a single data point in someone else's survey. So where does that leave the giants of Scutum? Both UY Scuti and Stephenson 2DFK1 are living on borrowed time. Current models suggest that stars like these will eventually contract and reheat, evolving into yellow hypergiants, luminous blue variables, or Wolf-Rayet stars driving fierce winds that strip away their outer layers and expose their cores. And then, when the core finally begins forging iron, the balance between gravity and radiation fails and the star collapses in on itself. A supernova. For Stephenson 2DFK1, that ending could arrive tomorrow, or in several thousand years. From 19,000 light-years away, we have no way of knowing whether it has, in some sense, already happened, whether the light of that explosion is already crossing the dark toward us. And maybe that's the right place to end this. Not with an answer, but with an honest accounting of what we actually hold. We know these stars are enormous. We do not know exactly how enormous. We know one of them may be violating a law of stellar physics that has held since 1961, or that our measurement of it is simply wrong, and we can't yet say which. We know stars eat planets, because we have watched it happen once, and read the chemical confessions of others. We know our own sun carries the same appetite on a 5 billion year fuse. A century and a half ago, astronomers in a quiet room in Bonn wrote down a number next to a faint orange dot and had no idea they were cataloguing a fire large enough to hold every world humanity had ever known. We are better at counting now. Our instruments can weigh starlight from across the galaxy and detect a single element out of place. But the giants of Scutum still keep their secrets, their true size, their true distance, their true nature, all still flickering at the edge of what we can measure. So astronomers keep watching. The same act, unbroken, from handwritten catalogues to space telescopes, pointing our instruments at the shield, waiting for the giant to give something away. And somewhere out there, wrapped in its own dust, a star bigger than everything we have ever known is quietly rehearsing the ending of every solar system, including the one you're sitting in right now.